Okay. During the formation of during the formation of during the formation of complexes during the formation of complexes n minus 1d ns np and nd orbitals hybridized to form vacant or empty hybrid orbitals which accept lone pair of electron in hybrid orbitals to form complex. During when the if n minus 1d if n minus 1 d ns and np orbitals are involved in the formation of complexes then it will result in the formation of outer orbital complexes. Inner orbital complexes. It involves in the formation of inner orbital complexes. And the inner orbital complexes are low spin complexes. And low spin complexes are spin paired complexes. That means spin pair means there is no unpaired electron. And the last one is if it is an inner orbital complex or a low spin complex or a spin paired complex, that means they are formed in the presence of strong field ligands. That means they are formed in the presence of strong field ligand. That means they are formed in the presence of strong field ligand. If NS, NP and ND orbitals are involved in the formation of complex, then the complex form are outer orbital complex, high spin complex, spin free complex, and that involves the WFL, that means weak field ligand. If NS, NP, ND orbitals are involved in the formation of complexes, then it will result into the outer orbital complex, outer orbital complexes, and next is high spin complexes, high spin complexes, high spin complexes, and spin paired complexes, spin paired complexes, and formed in the presence of WFN, weak field ligand, formed in the presence of WFL, weak field ligand. Okay. The geometry of the complexes, according to the BVT, the geometry of the complexes is determined by the magnetic properties of the complexes. But there is no involvement of hybridization in the determination of geometry. Determination of geometry. Geometry of the complexes is determined by the geometry of the complexes determined by the magnetic properties of the complex then hybridization does not involve in the determination of geometry. Hybridization does not involve in the determination of geometry. Hybridization does not involve in the determination of geometry. If the coordination number of the complex is 4, that means it having a two types of geometry. First one is tetrahedral geometry and the second one is square planar geometry. So if coordination number is equal to 4, that means it having two type of geometry. First is tetrahedral geometry and the second one is square planar. If it is tetrahedral, then sp3. If it is square planar, then it is dsp2. Let us take an example to understand valence bond theory. The first example is NiCl4 2-. Example number 1. NiCl4 2-. As we observe that the coordination number of this complex is 4. So coordination number is 4. It having either sp3 or dsp2. So we have to find it is sp3 hybridized or dsp2 hybridized. As we see that the oxidation state of nickel in this complex is +2. So nickel is in +2 oxidation state, and the electronic configuration of nickel 2 plus is 3d8 4s0. 3d8 4s0. Okay. Now the nickel 2 plus orbitals of nickel 2 plus ion. What are the orbitals of nickel 2 plus ion? 3d 3d8 4s2. As we know that Cl minus is a WFL, weak field ligand. Cl minus is a WFL. Cl minus is a WFL, weak field ligand. So no pairing. Okay. This is your 3d. This is your 4s. This is your 4p. 4p orbitals. Hybrid orbitals of nickel 2 plus are hybrid orbitals of nickel 2 plus are hybrid orbitals of nickel 2 plus three D 1 2 3 4 5 6 7 8 4s and 3p orbitals. 1s orbital and 3p orbitals are the hybrid orbitals. So it is sp3 hybrid. sp3 hybrid. The complex is NiCl4 2 minus. NiCl4 2 minus is a high spin complex. High spin complex. How it is formed? 1 3D, and this is your sp3 hybrid. Four pair of electrons from 4 pair of electrons are coming from the 4Cl minus ligand. Okay. Now we have to, it is a high spin complex, that means it is a outer orbital complex. Outer orbital complex. If it is a outer orbital complex, that means it is a spin free complex. High spin free complex. Spin free complex. Spin free complex. spin free complex. And is it paramagnetic or diamagnetic? We find that it is a sp3 hybridized. Hybridization is sp3 and it is a tetrahedral geometry. Tetrahedral geometry. Is it paramagnetic or diamagnetic? Here two unpaired electrons are there. That means it is a paramagnetic. Yeah, paramagnetic. How to find the magnetic moment? If it is a paramagnetic, then we have to find the magnetic moment using the formula mu is equal to under root n plus 2, under root n plus 2, where Bohr magneton. Bm is the unit of magnetic moment, mu is the magnetic moment, where n is the number of unpaired electrons in complex or in hybridized orbit. Okay, let us take another example. NiCO4 2 minus. NiCO4 minus NiCO4. Second one is NiCO4. NiCO4 complex. Here CO is a carbonyl ligand, which is a strong field ligand. Again, we observed that the coordination number of this complex is 4. So it is either sp3 hybridized or either dsp2 hybridized. Okay. So nickel is in zero oxidation state in this case. What is the electronic configuration of nickel 0? 3d8 4s2. Orbitals of nickel 0 are 1, 2, 3, 4, 5, 6, 7, 8. 3d 4s and 4p. Okay, as carbonyl is a strong ligand, so these electrons are transferred to, so spin pairing occurs. Okay, hybrid orbitals of nickel. What are the hybrid orbitals of nickel? Are sp3, one of the s orbital and 3 p orbitals are the hybrid orbitals. Okay, these are the sp3 hybrid orbitals. These are the sp3 hybrid orbitals. The complex is NiCO4 is a outer orbital complex. That means it is a low spin complex. low spin complex, that means it can accept 4 pair of electrons accept 4 pair of electrons 1 2 3 4 5 6 7 8 4 pair of electrons from 4 CO ligands. Okay, hybrid orbitals accept 4 pair of electron from 4 CO ligands. Okay, low spin complex, spin paired complex, spin paired complex, outer orbital complex. All spins are paired, means all electrons are paired, none of them is unpaired. And spin paired complex, it is an outer orbital complex, as outer s and p orbitals are involved, as there is no involvement of inner d orbital, that means it is an outer orbital complex. Outer orbital complex. Paramagnetic or diamagnetic, as no unpaired electron, that means it is a diamagnetic. Mu is equal to 0, that means it is a diamagnetic. And it is a tetrahedral. Hybridization is sp3. Okay, how it is tetrahedral? Ni CO 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 CO. It is the tetrahedral geometry. It is the tetrahedral geometry. Okay. Let us take another example. Ni CuNH3 whole 4 pi positive. Example number 3. CuNH3 whole 4 di positive. As again it is a coordination number is 4, it is either sp3 hybridized or dsp2 hybridized. Coordination number is 4, it is either sp3 hybridized and dsp2 hybridized. Okay, cobalt is in +2 oxidation state and the electronic configuration is 3d9 4s0. 3d9 4s0. Orbitals of copper are orbitals of copper 2 plus r. Orbitals of copper 2 plus r (3d). 9 electrons are there in 3d orbitals, and 4s orbitals do not have any electron. 4s, and this is your 4p. Hybrid orbitals of Cu2 plus. Hybrid orbitals of Cu2 plus r. In case of copper 2 plus, this electron is transferred to the p orbital. Okay, so one, two, three, 4, 5, 6, 7, 8. One of the d orbital is vacant and the ligands are 4, and the hybrid orbitals are one of the d orbital, one of the s orbital, and two of the p orbitals are involved in the formation of hybrid orbitals. This is your dsp2 hybrid, and one of the p orbital is remaining, 4p, where one electron is present, and this is your 3d. Okay, now the complex is CuNH3 whole 4 dipositive. Okay, it is a outer orbital complex, yes, and it is a outer orbital complex. It is an inner orbital complex. Inner orbital complex. This is your inner orbital complex. Inner orbital complex, and one unpaired electron is present. That means it is a paramagnetic. And mu is 1 plus 2, that is under root 3 Bohr magneton. Magnetic moment is root 3 Bohr magneton. Hybridization is dsp2. Geometry is square planar. Okay, now let us take another example, which is CuNH3 whole 4 2 positive, NiCN4 2 minus, NiCN4 2 minus. Cn minus is a strong field ligand. Yes, we know that Cn minus is a strong field ligand. NiCN4 2 minus. NiCN4 2 minus. Again we observe that Cn minus is a strong field ligand and the coordination number is 4, so it is either sp3 or dsp2. It is obvious that if it is a strong field ligand, then it is a dsp2 hybridized, we observed from this example. So let us see how. Nickel 2 plus gives, nickel is in plus 2 oxidation state and the electronic configuration is 3d8 4s0. 3d8 4s0. Okay, orbital of nickel 2 plus, orbital of nickel 2 plus are 3d how many electrons are there? 8 electrons are there, and 4s, and this is your 4p. Orbitals. Okay, now the hybrid orbitals of nickel 2 plus are, as it is a strong field ligand, so these electrons are pairing up, and Cn minus is a strong field ligand. Cn minus is a strong field ligand, so it So pairing will occur. So pairing occurs. These electrons pair up. Pair up. Then one of the d orbital and one of the s orbital and two of the p orbitals are involved in hybridization. It is dsp2 hybrid. dsp2 hybrid, and one of the p orbitals remain as it is. This is your 3D. The complex NiCN4 2 minus NiCN4 2 minus is a low spin complex. Low spin complex as all the electrons are paired. Low spin complex as all the electrons are paired. One, two, three, 4, 6, 7, 8. Four pair of electrons from 4 Cn minus ligand, 4 Cn minus ligand, 4 cyanide ligands, okay? And this is 4p. Low spin complex, spin paired complex, and it is a inner orbital complex. Spin paired complex, inner orbital complex, inner orbital complex, inner orbital complex. Paramagnetic or diamagnetic? It is a paramagnetic because there is no unpaired electron. Diamagnetic because there is no unpaired electron. Diamagnetic. Hybridization is dsp2. Geometry is square planar. Square planar geometry is Ni Cn 2 minus. This is your square planar geometry. Okay, now we are going to move with coordination number 6, where octahedral complexes are formed. Okay, if it is a octahedral complex, that means coordination number is 6, then hybridization is D2sp3 or sp3d2. There are two types of hybridization in octahedral complexes. If it is D2sp3, that means it is an inner orbital complex. If it is a sp3d2, that means it is a outer orbital complex. And outer orbital complexes are high spin complexes, and inner orbital complexes are low spin complexes. Complexes of coordination number 6. If coordination number is 6, that means the geometry is octahedral, and it is outer orbital or inner orbital, and the hybridization is D2 sp3 and sp3 D2. These are the inner orbital complex and these are the outer orbital complex. Inner orbital complex, outer orbital complex. Let us take example of inner orbital complexes. Inner, first of all we are going to take outer orbital complex. Outer orbital complexes. Outer orbital complexes. In case of outer orbital complex, the hybridization is sp3d2. So example number 1, COF6 3 minus. As we see that coordination number is 6, it is either d2 sp3 or sp3 d2. And cobalt is, in this case, cobalt is in +3 oxidation state. +3 oxidation state. So the electronic configuration is 3d6. Yes, 3d6 4s0. So orbitals of CO3 plus. Orbitals of CO3 plus are d orbitals, which is 3d, 1 2 3 4 5 6. F minus is a WFL. F minus is a WFL. So no pairing, no pairing, कोई pairing नहीं होगी. Okay, 3d, this is your 4s and this is your 4p. This is your 3d, 4s and 4p. And the hybrid orbital of hybrid orbitals of CO3 plus R. Okay, these are 4d orbitals. 1 2 3 4d orbitals. Okay, so it is 3d orbitals as it is. 1 okay, and the hybrid orbitals are formed by 1 s orbital, 3 p orbital and 2 d orbitals. These are involved in the formation of hybrid orbitals. sp3d2 hybrid. This is your 3d and this 3d orbitals are not involved in hybridization. 4d. Okay, this is your 4d. And the complex is COF6 3 minus. COF6 3 minus is a outer orbital complex and high spin complex. high spin complex. High spin complex, how it is formed? Hybrid orbitals, 6 pair of electrons, 1 2 3 4 5 6, okay, 6 pair of electrons one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 pair of electron, 6 pair of electrons from 6 F minus ligand, from 6 F minus ligands. Okay. Now what we observed, that it is a high spin complex. That means outer orbital complex, outer orbital complex, outer orbital complex. Number of 4 unpaired electrons, 4 unpaired electrons are present. That means it is a paramagnetic, 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 and mu is equal to under root of 4 plus 2 are 24 under root of 24 Bohr magneton. Okay, and hybridization is sp3d2, sp3d2. That means it is a outer orbital complex, and okay, low spin or a high spin. Okay, हो गया. Spin free or spin paired? Spin free, spin free. Okay, now I am going to draw the structure, geometry. CO F6 F. Okay, this is your octahedral complex. Let us take another example, FeF6 3 minus. FeF6 3 minus. FeF6 3 minus. FeF6 3 minus. Okay, this is your Fe is in +3 oxidation, iron is in +3 oxidation, so the electronic configuration is 3d6 4s2, out of this 3d5 4s0, and F minus is a WeFn, so no pairing. Here iron FeF6 3 minus. ओके, लास्ट एग्जांपल में भी 3 माइनस आएगा. ठीक है, नो पेयरिंग. ऑर्बिटल्स ऑफ Fe3 plus. F minus is a WFN. Okay, everything is correct. Now hybrid orbitals of Fe3 plus. Fe3 plus WFN, no pairing. Okay, same. In this case, FeF6, it is a high spin complex, outer orbital complex, paramagnetic, mu is equal to under root 24 Bohr magneton, sp3d2, and spin free. Everything is correct. Now taking an example of inner orbitals complexes. One of the example is FeCN6 3 minus, FeCN6 4 minus. Okay, start now. Next example is inner orbital complexes. Inner orbital complexes. Inner orbital complexes are Fe, Cn6. Number 1, Fe, Cn6, 4 minus. FeCN6 4 minus. In this case, we find that coordination number is 6. That means it is either sp3d2 or d2sp3. And we find that the oxidation state of iron is +2. Iron is in +2 oxidation state. Okay. Here iron is in +2 oxidation state. And the electronic configuration of Fe2 plus is 3d 6 4s 0. Orbitals of Fe2 plus ion are (3d) 1 2 3 4 5 6. As we know that Cn minus is a strong field ligand, so pairing occurs. Cn minus is a strong field ligand, so pairing occurs. 3d, this is your 4s, this is your 4p, and this is your 4d. Okay. Now the hybrid orbitals of Fe3 plus ion, hybrid orbitals of Fe3 plus R here pairing occurs as Cn minus is a strong field ligand. Okay, 2d orbitals are vacant from 3d, so these are involved in the formation of hybrid orbitals. 2 orbitals from the d, 1 and 2, and one of the orbitals from the s, and 2 orbitals from p, 3 orbitals from p. Then the hybridization is d2sp3. As d2sp3 hybrid. FeCN6 4 minus. This is a inner orbital complex, low spin complex. Low spin complex. Low spin complex. That means how it is formed? Six pair of electrons from 6 Cn minus ligand. 6 Cn minus ligands. 6 pair of electrons from 6 Cn minus ligand. That means, okay, 4d. This is your 3d. Low spin complex and spin paired outer orbital or inner orbital. We observe that it is an inner orbital complex. Inner orbital complex. Inner orbital complex. Okay. inner orbital complex, and in this case what is this? Paramagnetic or diamagnetic? Diamagnetic. Mu is equal to 0, diamagnetic. Okay. Hybridization is D2sp3, octahedral, spin paired or spin free? Spin paired complex. Draw the structure. Fe, Cn, 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 Cn. Four minus. Okay. Let us take another example. FeCN6 3 minus. Okay. Now we are going to solve more examples in tomorrow's class. Before winding this, we are going to learn some of the limitations of this theory, and in next class we are going to discuss more questions on this concept. Okay. Limitations of BDT are. What are the limitations of valence bond theory? We observe that it is unable to explain the quantitative interpretation of the magnetic data. Unable to explain the quantitative interpretation of magnetic data. Limitations of BVT. First limitation is that it is unable to interpret the quantitative magnetic moment. Unable to give the quantitative interpretation of magnetic data. Second is unable to give the reason for the color and coordination complex. Why the coordination complexes are colored? Valence bond theory does not explain. This is explained by the crystal field theory. Unable to explain why coordination complexes shows color. Unable to explain why coordination complexes shows color. Third, unable to give quantitative interpretation of kinetic and thermodynamic stability of complexes. It is also unable to differentiate between strong field ligand and weak field ligand. Unable to differentiate strong field ligand and weak field ligand. Okay. Next, it also unable to explain the it also ये एक्सप्लेन नहीं कर पाया कि टेट्राहेड्रल और स्क्वायर प्लेनर कॉम्प्लेक्स में कोई डिफरेंशिएशन नहीं था इसके अकॉर्डिंग. अनेबल टू डिफरेंशिएट between the tetrahedral and square planar complexes in coordination number 4. These are the 5 limitations of this valence bond theory. That first of all, the first one is it is unable to differentiate between outer orbital complex, differentiate between tetrahedral and square planar complexes in coordination number 4, and it also unable to give quantitative interpretation of kinetic and thermodynamic stability of the complex, and also do not explain why the coordination complexes are colored, and it also does not give quantitative interpretation of magnetic data. All these are the limitations of valence bond theory. That's all for today's class. So we are going to revise what in today's class we have studied. First of all, we studied about the bonding. So first of all, the bonding theory was given by theory for bonding was given by Barnard, and he is unable to explain why some element form coordination complexes, and he also unable to explain magnetic and optical properties of the complexes, and he also do not give any information about the directional property of the coordination complexes. Then we are going to study that how the valence bond theory involves the interactions between the metal and ligand. The interaction between the metal and ligand is purely covalent, and then we say that Ns, Np, N-Bundy and anti orbitals are involved in the hybridization, and then we find that the magnetic data geometry of the complex is determined by the geometry of the complexes is determined by the magnetic properties of the complex, and hybridization does not have any role in the determination of the geometry of the complex. Then we find the how it is outer orbital complex or inner orbital complex. Then we talk about paramagnetism or diamagnetism, and we also find the formula that mu is equal to under root n plus 2, and then further we are moving to the octahedral complexes, where we study some few examples. One of the example is F6 3 minus, and one of the example is COF6 3 minus, and another one is FECN6 4 minus. Okay, and in next class we are going to talk more examples. That one of the example is CONS3 whole 6 3 minus, CONS3 whole 6 3 plus, and CONS3 whole 6 2 plus. We are going to differentiate between these two, that cobalt 2 plus is ammonia act as a strong field ligand in case of +3 oxidation state, and cobalt act as ammonia act as a weak field ligand in case of +2 oxidation state. In next class we are also going to talk about that palladium 2 plus and platinum 2 plus and your Au 3 plus always form complexes which are square planar complexes, and it does not depend on the strength of the ligand. If it is a weak field ligand, it is always forming a square planar complex. If it is a strong field ligand, then it is always forming a square planar complexes. Okay, thank you students, see you in next class. Bye bye.